Hi, I'm Dave McDonnell, and I'd like to welcome you to Storage Fundamentals 101. The objective of this content is to help early technology professionals or technology enthusiasts to learn more about the basics of enterprise storage and to get past a lot of very confusing jargon. To help you understand storage fundamentals, we're going to talk about what storage is. We'll talk about storage media. We'll talk about storage types between block, file, and object storage. We'll talk about what I'm going to call the early storage locations, and then we'll talk about newer storage locations. And by the end of this, you'll be ready to have a conversation with anyone. Before we get started, let's talk about storage. It's actually pretty simple. Everyone is using storage today in some form, if you have a phone, a tablet, or a personal computer. But enterprise storage has a lot of jargon that can make it confusing. It's important to have some flavor of what this is all about because storage is becoming the bottleneck in IT workflows. So your knowledge is going to help you. It's going to help you help your organization or help you help customers, your stakeholders, whoever those might be. So we'll get you past the jargon so you're empowered to have a conversation with anyone about enterprise storage. So let's begin. So what is storage and why do we have it? Well, let's say it does three important things. So it feeds data to the computer's processors so that the job, the work, whatever it is you want to happen can occur. The second thing is it will store the results, sometimes temporarily, and hopefully, in many cases, keep the data on an ongoing basis, and it will protect the data from being lost. Customers have cared about protecting data for a long time, and most vendors in the storage industry, they do a pretty good job of this. But when it comes to feeding data to the computer's processors, that's getting harder and harder. Why? Well, NVIDIA is making very, very fast GPUs, and there's a whole host of other manufacturers making a lot of very fast accelerators used for AI or high-performance computing. And now scaling that performance, that's difficult. And most vendors don't do a great job of doing that. Okay, so we know what storage is now. Let's take a look at storage media. Data gets put onto what we call storage media. Now, a lot of this you're already going to be familiar with. In the world of personal computing, we have flash-based cards that we put in our cameras or USB sticks that we might be pulling in and out of our PCs or entertainment devices. And then we have hard drives or flash drives. Now, they can be inside your computer or they can be attached externally as an external drive. Well, those building blocks are what we see over in the world of enterprise computing as well. So there's disk, flash, and tape. The two oldest are disk and tape. They date back to the 1950s. Flash started coming on in the 2010s, but those are the three main sources of media today. So disk is older, it's more prevalent, it's still arguably lower cost than per terabyte or per petabyte compared to flash, but flash is coming on strong and the roadmap keeps getting better and better. The world seems to be moving more so and more so towards flash because it consumes less power and there's less power out there. And then the ultimate in terms of density and low power is tape, which has been around since the 1950s, but is still growing because there's nothing that's lower cost, there's nothing that's denser, and there's nothing that has a longer shelf life. So you'll see here, disk drives generally have 3 to 5 years of shelf life or operational life. Flash can go 7 to 10 years. Well, those tape cartridges, they can go 10 to 30 years. If you're curious, there's a lot more data on each of these with some examples and the history. They're not germane or important to being able to have a good storage conversation. If you're curious, this is going to be here for you, but I'm not going to spend any more time on it here. Now, you will hear temperature being used with storage. You'll hear about hot storage or cold storage or warm and cold storage in between that. So hot storage is your high performance storage. It's the storage that you're accessing frequently. It's what you're using in active databases. It could be where you're processing transactions for customers. So you're accessing this data frequently. You want performance to be very quick. You're most likely using flash media to satisfy applications in this space, but you don't want to put all your storage into hot storage. Why? Well, as you can see in the middle here, it's the most costly of the different media types. Let's go down to warm storage and cool storage. You could be using low-cost flash media. You're more likely using spinning magnetic disk. Of course, this is going to change over time. And then for cold storage, you're probably using tape. Tape is the least expensive, longest shelf life, and consumes the least energy. Now, I've got a little jargon alert here. Latency, right? Latency is your access speed, right? It's the delay from the time you make the request for the data to the time it gets turned around for you. So, as you would expect, flash is the fastest with the lowest latency. Tape has a higher latency. A little fun fact, it actually transfers data, transfers data quite quickly, but there's a time where it has to go load the cartridge and get to the data before it starts transferring the data, which makes the overall latency relatively slow. Now we're going to get on to the types of data and storage. Let's talk about data. There are two types of data, structured and unstructured. Structured data is what's used in a lot of the applications you can think of and name today. Your driver's license system, your student information system, maybe your patient record system. The data is put in spreadsheets, and there's a few examples of database suppliers here, or spreadsheets also use structured data. Unstructured data, which is about 80% of the data that's out there today, is all of different sizes, right? So this is the data that you get from word processing documents, images, video, sounds, things like voicemails, or videos. There are many examples. Unstructured data is most of the data on planet Earth today. It's also the one that's growing the fastest. It's also the one that's the most difficult to deal with. So now we've talked about the data, let's talk about the types of storage. And this is the way the data gets written onto the media. So there are three: block, file, and object. Block storage is what you think of with structured data. This is where you're using blocks that are all the same size. And think of applications where you have first name, last name, address, cell number, telephone number rather, and email address. File is usually used for unstructured data, or potentially a combination of unstructured and structured data. And this is where you have your word processing documents, your presentations, videos, and file has been around a long time. So this has been storing unstructured data for a long, long time. Performance level, not quite as fast as block, but there are tools that optimize file-based data for performance. So it's actually quite popular in some of the largest data sites in the world today that are requiring extreme performance. Object storage is optimized for unstructured data, and you store all your unstructured data in it. You use metadata, or think of it as an address, to figure out where that data is and retrieve it. So it's optimized for simplicity, and it's optimized for scale. But as you'll see in the bottom here, not necessarily optimized for performance. So there you go, block, file, and object. But we'll spend some more time on these and give you some examples. Let's go a step further with file and object storage. File storage is a hierarchical system. It uses a series of folders to help you find a pathway to your data. So you or your application needs to know where that file is located or where that data is located. Object storage is a little bit different in that you put all your data into it, but you need an object ID, or think of it as the address, to be able to find the data so that you can retrieve it. This might be a little confusing, so let's keep going and give you some examples. So analogies are helpful. Think of block storage like a bunch of blocks of all the same size. Block storage isn't very intelligent, right? Sorting out these blocks and doing something meaningful for it requires software that will sit in the controller or sit in the operating system. But think of blocks literally like blocks. Whereas file storage, you have to know where things are. Remember how it's hierarchical? So you could say, all right, I've got an example here of a set of filing cabinets or lockers, right? So I need to know which filing cabinet to go to. In the filing cabinet, they have folders. Then I need to get to the right folder, and inside the folder is the document, and the documents are all of different sizes. With object storage, think of the warehouse. Maybe someone sent you a package and the courier tried to drop it off at your house but wasn't able to. So they left a ticket and you go to the courier's warehouse and you hand them a ticket. And they are able to find your package just based on your ticket number. Or you can think of this as well as the dry cleaners. You go to the dry cleaners and you hand them a ticket. They can find your package of clothing based on your ticket, maybe your last name or your phone number. But you don't know where it is in that warehouse. Is this confusing? If so, let's go. Sometimes the parking lot analogy is helpful to explain the difference between block, file, and object. With block storage, you're showing up and you're parking in the same place every day. You have the same car in the same space. Everyone has the same car, the same size. Everyone parks in the same spot every day. The analogy of a parking lot with file storage is that you show up, you park in whatever space is available, but you have to remember where you left it so that at the end of the day or the end of your visit, you know where to retrieve your car so you can go back home. With object storage, that's the valet. So you show up, you drop off your car, you hand the keys to someone, they give you a ticket, you go and do whatever it is you're going to do, and then you use your ticket to hand it back to the attendant, and they use that to go locate your car and bring it back to you. You don't know where it's parked. So let's move on and get to storage protocols. So storage protocols get the data in and out of storage media. Let's take a look at this with a picture. So you have a user that will request a job or a file. They'll do something that requires data. That data will get retrieved from the media, right? It could be flash, disk, or tape media. It could be written in block, file, or object format, right? And it gets in and out of the media using a protocol. Think of it as a pathway, the way the data travels from the media to the requester, right? So in this case, it'll get loaded into the memory on the server, and the user will be able to see it and interact with it. So storage protocols are what we use to get data in and out of the media. It's the language that is spoken to help them get from the media into the memory. So this can be intimidating, but let's simplify this for you. SMB, or the server message block, think of that as the file system used by users of Windows. Likewise, people of Linux or Unix operating environments, they use NFS. And then if you're doing cloud storage, you're probably using some S3. The cloud providers really made S3 more popular and more relevant. As you can see, it's a younger protocol, but wow, has it grown quickly. You'll see in data lakes, HDFS, or the Hadoop data file system. That was very big in the 90s, very big, and grew quickly in the 2000s, even in the early 2010s. But most people are moving their data out of HDFS data lakes into more modern data lake houses, most frequently with the S3 protocol that they'll use to get data in and out. There's another one that's specific to accelerators or GPUs. This one's made by NVIDIA to allow data to go directly from the storage directly to the GPU buffer. And that's called GDS, or GPU Direct Storage. And then there's CSI, which is Container Storage Interface. So these are for applications that are modernized or written to be run in containers, and the way they get data in and out of storage is through CSI. Let's talk a little bit more about Hadoop data lakes. First of all, it originated at Google as a project to help you scan log files across a lot of servers. Well, log files, what are those? Well, remember that Google reinvented advertising, and their big claim to fame was that they would charge you only when a customer clicked on your ad, not just for an eyeball. To be able to measure whether someone had clicked on one of those ads, they had to invent a protocol to be able to go and measure that. And that's where this came from. It went from Google to Yahoo. It got put out into open source, and then there were some commercial customers that made this really robust for the enterprise. So those companies were Cloudera, Hortonworks, or MapR. Cloudera is the only ones remaining of those today. Now, this allowed customers to get going quickly. They would use servers with a lot of disks in them, or what we call storage-rich servers, and they would add 1, 2, 3, 10, 16. It allowed them to get going very quickly and eliminated the cost of the high-speed network. It was wonderful to get going, but it was expensive. It was difficult to manage at scale. You would have to have several clusters. You would then have copies of the same data in some of those different clusters. And then you had to manage different versions of the data. At the end of the day, this is just too hard to manage. So most customers are moving away from these. Most of them, as they modernize, are going to go to data lake houses, which can do structured and unstructured data. And most frequently, or most likely, they'll be using Object S3 as the interface instead of HDFS. So it's not relevant for a new company that's starting tomorrow, but there's a lot of HDFS still in use today. So it is good to understand this, because you could help customers modernize and move their data from an HDFS data lake to an Object S3 data lakehouse, as an example. And I'm going to mention a little bit more on a couple of protocols here. First one I'm going to talk about a little bit more is container storage interface. So the world is changing the way it writes software. Instead of writing in the traditional manner, long monolithic applications, they're writing them to be cloud native. And when they're written to be cloud native, they write small pieces of code, or what they call microservices. Those microservices run in what we call containers, and then those containers get orchestrated via Kubernetes, or the commercial version of which is Red Hat OpenShift. Well, applications need to have data. And the way that they get the data in and out of the storage is through that container storage interface. So most storage today is being built to have the ability to interact with CSI. So you're going to get asked that question, or if you hear that terminology, now you understand what it is. Because this is for all modern applications, it's going to be very prevalent and important out there. Let's go to the next one. NVIDIA came out with GDS to optimize usage of their GPUs, the accelerators that are very well known, very prevalent around the world, and commonly being used with AI or high performance computing. So GDS is a storage protocol because it helps to move data from the storage directly to the GPU. And that frees up the CPU so the CPU can do other work. So it saves time and it frees up CPU cycles for other work. So it's wonderful for people who have those NVIDIA GPUs. The only challenge is people may need to have their applications written to take advantage of it. So just a little more context on a couple of important protocols. Now, that takes us to a new section called early storage locations. So we'll take a look at these and get you familiar and comfortable with these locations or topologies. So let's talk about how storage gets connected to a server. You're going to hear acronyms of DAS, SAN, and NAS. Are those confusing at first? Well, of course they are, but I'm going to make these simple for you. Direct attach is as it would imply. You attach the storage directly to the computer. Storage area network, well, we hear the word network, so the storage gets attached to a network switch, and the network switch gets attached to the server. Now, it's a switch, so you can have multiple servers, and you can have multiple storage systems. And then network attach is, as the name implies, storage attached to the network. So let's take a look at a picture of this to make it even simpler. Direct attached storage is shown here. You can have a computer attached directly to a storage. These are some of the different interfaces on how this would happen. This is your USB interface to a USB stick, or it could be a Thunderbolt connection. SATA is to the motherboard, or eSATA. SAS is high performance. That's most commonly what you see in the enterprise today. But direct attached storage, you can think of some simpler, more consumer-friendly examples, right? Your phone or your laptop. or a tablet if you have one. Those are all DAS devices where the storage is attached directly. With storage area networks, you can see here we have a server. We could have 2 or 3 connected to different ports here. We have our network switch, and we have the storage attached to the network switch, or we could have several attached to the different ports here. So that's SAN. Now, network storage is, as we explained, attached to the network, and you can see here I have servers of different types attached to the network, right? Ethernet is the most common topology used or protocol used for networking. And if I hang the storage off the network, now all the users of all these different environments, they can see it and they can start using it immediately. Let's dig a little bit deeper into SAN topology or SAN location. So, as I explained before, a SAN storage system can be used by more than one computer. In this diagram here, we have 3 servers attached to 3 different ports on your SAN switch. The SAN switches are most frequently fiber channel, which means very, very fast. And you'll see here that in one system, we've carved this out into what we call logical unit volumes, or LUNs. And server 1 has a piece of the storage system, and you can see it here in blue. Server 1 talks to the data, uses the data in section 1, or LUN 1. Server 2 has LUN 2, and server 3 can only see the data in LUN number 3. Makes sense, right? So now I have one switch, I get very high performance, dedicated path to my data, and so it's great because it's fast, but it's hard to manage at scale. And I'm going to issue a jargon alert here, right? So LUNs we already explained. You might also hear of volumes, which is a group of LUNs. You might also even hear zoning, where you're dedicating paths to ensure very high performance for critical applications. SAN is wonderful technology. It's most frequently used with block storage applications, and people really, really like it for their most critical applications, but it's not very flexible because you can only see the data that you have assigned to you in a LUN or a volume. So it has its pros, but it has its limitations. Okay, so now we talk about network attached storage, or NAS, and wow, it's a wonderful concept, right? You put the device on the network, you feed it a power cable and a network cable, and you can start downloading data onto it right away. Well, it is wonderful, and it's very easy to get started. The problem is you keep going and going and going, and now you are managing a lot of different devices. This talks about an example here where one customer had 48 NAS devices, or in this case, the manufacturer was NetApp, and they called them filers, 48 NetApp filers serving data to users off of one cluster, right? So this gets very hard to manage. And when you have 48 different devices to manage, you probably have the same data replicated in more than one of these places. If you have teams sharing a NAS device, you have to watch the growth of them. And do you need to move one group to a different NAS? Do you need to order more NAS? A lot of it gets managed manually. It's very hard for a storage system administrator to keep up with that. So very, very good and easy to get going, very hard to manage at scale. Okay, so let's just do a recap on these early storage locations. DAS is great, right? Direct attached storage, it's great, but it's limited and it's not very easy to scale. Storage area networking, or SANs, are great, but they're expensive and they're also difficult to scale with, especially with unstructured data as it keeps exploding and exploding. NAS starts really, really simple, but becomes difficult to manage at scale. Well, those are early storage architectures. Now we're going to change gears and we're going to start talking about how we manage this growth of unstructured data and newer storage locations, and we'll get into concepts and explanations of software-defined storage, cloud storage, and storage as a service. Let's get to looking at modern storage locations. Okay, so let's talk about modern storage concepts and locations in one slide here. So let's start with software-defined storage. Software-defined storage separates software from the hardware. Okay, so a lot of devices, historically, they have a very expensive storage controller, and all the intelligence is in that controller, or In your laptop, it might be in your operating system. But in enterprise storage systems, it's in the controller. And the storage itself, remember the blocks, right? The block storage is dumb. All the intelligence is in the controller. Well, what if we, instead of putting the software in an expensive controller, use commodity CPUs to do that? So now I don't need an expensive controller in each of the storage devices, and I can have more centralized management. And maybe I can use that to manage multiple storage systems in software as opposed to managing individual devices. So this is where you have a pool of storage for an artificial intelligence center of excellence, or a shared HPC infrastructure, or potentially a data lakehouse as some of the use cases. So now you can start very small and you can scale very large. Hopefully, if your vendor has done a good job with the same user interface and the same set of management tools, it's simpler to manage. It's lower cost because you use it more efficiently and you have less replication, fewer copies of the same data. You have flexibility because if the intelligence is in software, you can use hardware from different vendors, so you don't have vendor lock-in to one platform. And now I get even more efficient resource management and centralized management. Great. So what are the disadvantages? Well, remember how easy it was to drop a NAS on the network or to install a USB stick for direct attached storage? Well, so this has a bit of a learning curve required because you have to learn the software and how to manage it. So software-defined storage. We'll spend some more time on that. But for now, let's leave it there and go to cloud storage. Cloud storage has the data sitting, you guessed it, in the cloud. Some of the common examples, Amazon Web Services has their S3 service, right? Remember we talked about object storage? Microsoft OneDrive, Box, Apple iCloud, those are all examples of cloud storage. They're used for all kinds of different use cases. Now, the advantages are you can get access to a lot of storage very, very quickly and very, very simply. Okay, so disadvantages, well, it can get expensive, especially with unstructured data. Remember, that's big, chunky, hard to deal with. It's also growing quickly. And your performance isn't going to be as predictable. So guess what? Your costs may also not be as predictable as well, depending on the charge model. So that's cloud storage. Well, let's talk about as a service. Okay, so you can hear STAS for storage as a service. You'll also come across XaaS, or everything as a service. And this is where you have vendor-owned storage sitting in your data center or one that you're renting. So now you're probably paying, you can pay however you want, but most frequently people are paying monthly. So now it becomes a part of OPEX, or operational expense, instead of CAPEX, or capital expense. So advantages, well, I don't have to put down all the capital to buy the storage, and I can wait until I get cash flow to pay for it as I go. I also can have options where it gets managed for me, and I can add to it as I need more, and I pay only what I use for. What are the disadvantages? Well, I might get locked into one vendor, and it can be difficult to change. Now, I'm also putting the responsibility for security of that data on the shoulders of someone else. Maybe that's okay. Maybe it's not. But also, this is going to be more costly than buying and managing storage yourself, because there's some overhead involved in running it as having a vendor run it as a service for you. Okay, so software-defined storage can be confusing at first. Well, let's step back for a minute. The whole world is getting transformed by software. We have software-defined phones. If you have an iPhone, as an example, wow, is there a lot of software in it and a lot of capability right at your fingertips. TVs are now smart TVs. Movies are software-defined, and you have smart TVs or smart devices that you can consume them on. The same is true of music. I'm guessing most people watching this have a banking application on their phone, so banking is becoming software-defined. Even watches now are becoming software-defined, or cars, and the list goes on and on. It's only natural that storage would get transformed by software too. So let's talk about what hardware-defined storage is. So remember, with SAN technology, I have a computer attached to a switch or several computers attached to one switch, and it could be attached to several storage devices. If I need more data, I add more hardware, and the software that runs these SANs is going to be embedded in the controllers inside those SAN devices. So they are wonderful, but they're pretty costly. Likewise, we love this concept of network attached storage. I just attach to the network and I can start loading data on it right away. Well, fantastic, difficult to manage at scale, but I'm still having to manage this as an individual device. By the way, if you want an analogy of how to think of this, NASs, you can think of them as like USB drives that you might have at your home. And if you want to protect your data, you probably want 2 copies. Well, if you want disaster recovery, you might need another USB drive and to take it to a friend's house or a relative's house so you can survive a colossal tragedy like a flood or a fire in your home. Anyhow, NAS devices are similar. So just as USB drives can be hard to manage and to provide data resilience for, NAS is hard. And as you add more storage, you add more systems, each of those becomes something that you need to manage unto itself. If you get to software-defined storage, you can get this concept of storage abstraction or virtualization to make several storage systems appear as one. So here, I'm showing a scenario where I've got a server attached to 3 different storage devices. Now, I'm making all of those look like one entity, and that entity, that chunk of storage, I can manage as one volume. That's where the intelligence is on software that's running on your computer, not software embedded in a storage controller. So, wow, now I can manage those 3 things as if it was one. Now, management is easier, it's automated, I have fewer copies of the same data, and it's also simpler to manage growth. So, there's an example of the benefits of software-defined storage. Now, let's get into these modern storage locations and concepts and talk about tiering. So tiering is an example of software-defined storage where you use policies to automatically move data from one storage system to another. And in this case, you can see we've set up 3 different tiers to store data in. We've got a performance tier where we want really fast performance. We're willing to pay the money for it. And then I've got an everyday tier where maybe I'm using NVMe flash at the top and I'm using spinning disk in the middle tier. And then, as you can see here, these are tape libraries. Maybe I'll have what I call a capacity tier and I'll put it on tape. And you can see there, wow, that's low cost. There's a reason, by the way, that this is green, right? Because this also saves a lot of energy because I have fewer copies of data. I need fewer storage systems to house them on. And if I'm using tape, these tape libraries, they only consume power when you're either writing data to the tape library or reading from that. Otherwise, they sit idle. So they're great if you have an energy bill that you're trying to manage and optimize. So the movement of data from one to the other is automated. Okay, so you could say, well, how about I move the data from the performance tier to the everyday tier if data hasn't been touched in a month? And then if it hasn't been touched in 2 months or 6 months or whatever policy you want to define, it'll automatically go down to the tape library. So there's an example of tiering and software policies doing this dynamically. Now, from a user standpoint, they see just one drive here. So in this example, I've got 2 NVMe systems. I've got 1, 2, 3, 4, 5, 6, 7, 8 disk systems, and I've got 2 tape libraries. But to the user, this just looks like a Finder window if you're in the world of Mac OS. Or if you're in Windows, you might call it a D drive. So it's very, very easy for users. They're just clicking on a file. They don't know where it is in the background. So, wow, what a great concept with tiering and as an example of software-defined storage in action. And I'll also make the point while we're here on tiering, it's not just tiering from one storage system to another or one type of media to another. You can also go in and out of the cloud, or you can go to other data centers. You can do this over a wide area network, or that's IT speak for data centers at different locations. So software-defined storage, yeah, wow, very, very powerful. So now let's get to the clustered file system as another example of software-defined storage. So with a clustered file system, you have users that do work and they submit jobs to a compute server or more likely a rack of servers. Those servers will be connected to the network, and now we have servers that can front running software connections to storage, but we're going to make that all look like one storage pool. Okay, so this is all one D drive or Mac OS Finder window to the users. So all users can see all the data, right? It's like what we talked about in tiering. So this is an example of the same capability, but with what we call the clustered file system. And then as an add-on to the clustered file system, there's a such thing as a parallel file system where it writes the data in parallel. Okay, so now in this example here, I've got a user saving some data, and that data is getting split up, in this example, to 4 different servers going into 2 different pools of storage. So if you have an environment where you've got hundreds or thousands of users, now I'm 400% faster, right? Because instead of writing these sequentially on one part of one drive, I'm writing them to different drives. So I'm 400% faster, 4 times faster. I can write 4 times faster. I can read 4 times faster. So as you can see here, why do we do this? To get better performance. We can also do this to get better resilience, efficient resource usage, and this is better for sharing data with many users. It's how we achieve scalability in large organizations. Let's take a look at what a NAS topology looks like next to a clustered file system. So as we explained with NASs, you buy a NAS, you fill it up, then you buy a second NAS. Now you've got 2 things to manage. In this example, you would have 4 different NAS devices to manage as 4 unique individual silos of data. In the parallel file system, you would have, let's say we have those same 4 devices, but they look like one pool. All users can see all data, so I simplify the management, but I also optimize the performance, and I give 4 times the amount of throughput in and out of those devices because I'm writing in parallel. So as you can see, we'll have a cute animation here that shows we can use that same hardware with a parallel file system to accomplish better performance, even using the same hardware. Okay, so let's get to modern storage locations and storage for cloud-native applications. We came across this before when we were talking about protocols, right? So the CSI protocol is used for containerized applications. Modern applications need modern infrastructure, and the modern storage for containerized application uses the CSI protocol. So here, I can have storage that sits inside of servers, or I can have external storage. Most deployments are actually a combination of the two, where there will be some internal disk used for operating system or other important functions. They might have some that are what we call storage-rich servers with a lot of drives in them, and then most of them will still need to access and write data to and from external storage pools. And the nice thing is we can get data that's in formats like block, file, and object, all with different pathways using the CSI interface into those containers to run those jobs. This is a little confusing at first, but just think of it as CSI as the way modernized applications get the data in and out of the media. And if you want to look at this broken down a little more simply, these modern applications, remember they're built from microservices. Those microservices, they run in a container. So here's a picture of some virtual containers, right? They're not physical containers. These are in software. And now I've got 3 different jobs that are running, and as they need to get data to run their jobs, they use this CSI interface to pull it out of either block, file, or object storage. Okay, let's come back to cloud storage briefly. The concept is very simple. The data sits in the cloud, but there's a bit of jargon here that I want to make sure you understand so you're not caught off guard. You'll hear the concept of ephemeral storage. Okay, or in the HPC world, they might call it scratch storage. This is temporary storage used while the job is running. Okay, so when the job is done and the user logs off, that data goes away and it's not saved. Okay, that's what we call ephemeral storage. Persistent storage is data that you keep after the job is done and after the user is logged out. That's what we keep for a long time. And then a lot of people use the cloud for archiving, and that's where we go back to our temperature conversation. So that's cold storage, right? Most frequently using tape. So wanted to come back to cloud storage just to make sure you were not going to get caught off guard with some of those jargon items like ephemeral or persistent storage. Let's get to storage as a service. And here we are with storage as a service, or STAS. The jargon you'll hear here is it could be as a service, it could be STAS, or it could be XaaS, which is everything as a service. Okay, so we covered this before, but this is important and it's growing quickly, so I want to make sure we quickly revisited those terms. So here we go. Our objective was to get you acquainted with some of the basics of storage fundamentals for how storage works in the enterprise. So we talked about what storage is, the media, locations, newer storage locations. That's a lot of jargon. We got you through a lot of stuff. Let's just take a quick recap of some of the key concepts. Media, there's disk, flash, and tape. The storage types or formats are block, file, and object for how data gets written to that media. We have this concept of temperature, from hot storage to warm, cool, and cold. We have some of the early storage locations or topologies that we covered, like DAS for direct attached storage, SAN for storage area networks, NAS for network attached storage. And then we had conversations about modern concepts and topologies, right? So the software defined storage approach, or clustered file systems, tiering, cloud storage, and as a service. We also got through protocols, and that's nothing more than weird acronyms that explain the pathways on how the data gets in and out of the media. So that's a lot of stuff. Look at you. You're empowered. So pat yourself on the back, go listen to your favorite music, go eat some ice cream or whatever it is you do to celebrate, because if you're here now, that means you got through a lot of challenging jargon. You're also empowered. You're smart. You're ready to have conversations with your storage people or storage vendors or people in IT. So pat yourself on the back and feel great. One last thing. If this was helpful to you, I want you to let me know. There's a lot in enterprise storage. This was the basics. There are some other topics here. I'm going to read them out to you, and you tell me what's interesting to you. So I've got other modern storage topologies. There's backup and archiving, disaster recovery, data resilience with RAID, storage for AI, innovations with storage, agentic AI, and data infrastructure. There's a lot going on in the world of data. So if there's enough interest, we'll consider doing some more of these. In the interim, I'm hoping you'll give me your feedback on what you thought of this course, or what your feedback is for what you think we should do next, by either clicking on that link or scanning that QR code and answering a few short questions. So other than that, I will thank you and wish you on your way to learning more about enterprise storage.